Suppose we need to go from point A, collect water from a river that flows in a straight line, and bring it to point B. What is the shortest path that we can take? Once we decide on the location point C where we are going to collect water, we might as well go from A to C in a straight line and then to B in a straight line. The total distance traveled along this path is the distance S1 from A to C plus the distance S2 from C to B. This total distance S is then a function that depends on the choice of C. And our goal is to find the point C on the river that minimizes S. One clever way to solve the problem is to realize that we can reflect point B across the river to point B prime. The distance S2 is then the same as the distance S2 prime shown here. The shortest path from A to B prime is just a straight path, and its intersection with the river is exactly the point C that minimizes S1 plus S2 prime, or equivalently S1 plus S2, which is S. Now, I'm not so good at finding clever solutions like this, but I will still like to recover this geometric intuition just by doing calculus. And this is where Lagrange multiplier method comes in. Let us free C from the line of the river. The total distance S is still a function of C, just with the whole space as its domain now. We can find the gradient of S by adding up the gradient of S1 and the gradient of S2. Let's consider S1 the distance of C from A. Its gradient is the unit vector pointing away from A because that is the direction in which S1 experiences the steepest increase, and the vector's unit because S1 increases precisely by the amount in which C moves in that direction. Another way to think about it is that the gradient is a vector perpendicular to the level set of S1 that C is on. The set of constant distance from A is just a circle centered at A, and it makes sense that the gradient is perpendicular to this circle. Similarly, the gradient of S2 at C is the unit vector pointing away from B. Adding the two gradient vectors give us the gradient vector of S. Now putting C back onto the river again, if the total gradient vector is not perpendicular to the river, let's say its component parallel to the river is pointing towards the right, then as we move towards the right along the river, the total distance will increase. Similarly, if we move in the left direction, we can decrease the total distance, getting shorter paths. Ultimately, we can find a point C where the total gradient is perpendicular, which means that there is no way to shorten our path anymore, and that will be the location C that gives rise to the shortest path. At this point, the horizontal components of the gradient of S1 and the gradient of S2 must cancel, and since they're both unit vectors, we know that the angles they form with the river must be the same. This is precisely what the reflection solution entailed, and we have recovered the geometric intuition using Lagrange multipliers. One of the great benefits of Lagrange multiplier is that we can easily generalize what we did. For example, what if we move slower after collecting water, and we want to minimize time instead of distance? What you will discover is known as Snell's law, which also relates the angle of incidence and the angle of refraction as light passes through two media in which light travels at different speeds. I'm leaving this one for you to feel the excitement of discovery for yourself. Instead, I want to talk about yet another brilliant application of Lagrange multiplier. Consider a painting with certain height attached to a wall at some distance above the ground. Your eyes are also at certain height from the ground, but less than that of the painting. How far should you stand away from the wall to maximize your viewing angle? First of all, the absolute distances from the ground of your eyes and the painting don't matter. Only their difference does. Let's call that h and the height of the painting t. Like before, let's put away the constraint and consider the viewing angle zeta as a function on the whole plane. We ask, what is the gradient of zeta? A small geometric fact that we'll use is that on a circular arc with two endpoints fixed, the angle formed by connecting a point on the arc to the two endpoints is constant. In case you haven't seen this before, this is known as the inscribed angle theorem. More precisely, the inscribed angle on the arc is exactly half of the central angle formed by the endpoints and the center. But back to business. We know that the level set of the zeta that point E lies on is exactly the circular arc that goes through the top of the painting, E, and the bottom of the painting. The gradient vector will be perpendicular to this arc and points inward because our viewing angle increases in that direction. The magnitude of the gradient doesn't matter. We just need it to be perpendicular to the constraint, the line of our eye level. This happens exactly when the arc is tangent to the line of the eye level. A little geometry allows us to figure out the answer. Isn't this beautiful?